So, yesterday we were talking about an ideal. If an ideal is contained in union of prime ideals, then it has to be in one of them, and similarly if an ideal contains prime ideal contains an intersection, then it should contain one of them. So, let us study more about ideals. So, today we will look at a specific kind of set. Suppose I have I be an ideal and S be any set in A. Okay. Then I can say that I can define a new set, which I will denote this by I colon j I colon s, to be set of all elements x in A such that x s belong to I for every s in S. Subset, any set. So, I am looking at all elements which will multiply S inside I. Okay. Or in other words, or in in a general sense, we are taking ideal I and dividing by all elements of S in some sense, right. We are looking at all x such that x s is in I for every s. So, we are taking all elements of the form x s and divide by s in S. That is vague meaning of taking colon. We will look at this, we will see. Okay, so, this is also, you can also write this as x in A such that x s is in I. Okay.
S belongs to S and S is a subset of A. I thought S is a subset of I.
No. So, let us look at some examples first, that will clarify few things. What happens if S is a subset of I itself? Then what happens to I colon S? It is a whole ring, right? Yeah. Every element of A now, suppose I take an element x in this one and y in this one. Can you say x plus y also belong to this set?
Yes, sir.
X s is in I, y s is in I, x plus y s is also in I, right. So, therefore, x is in I colon s. So, if x comma y is in I plus s, then x plus y is in I colon s. What can you say about its product? X y belongs to I colon s. So, therefore, can you say something more? It is a subring. So, now the question is this an ideal? So, if I take x in I colon S and I take an arbitrary element A in A, can we say that x A belongs to I colon S? X A S is same as A times X S. X S is in I. Therefore, A times that will again be in I, because I is an ideal. So, therefore, x A belongs to I colon S for every A in A. So, these properties say that I colon S is an ideal. Now, let us look at some simple examples. Let me take I. So, my ring is, let us say, any field, any PID, any field f and polynomial ring over f. Take I to be equal to x square and S is x. Yeah. Sorry, yeah, 1, I mean ideal generated by 1, that is A, yeah. So, what would be I colon S? I am looking at all elements in all polynomials in will 1 plus x be there? Right. So, this is x square. So, in some sense now you are saying all polynomials with constant term 0, and that is generated by, that is the ideal generated by x. So, what have we done? We have just divided. That is exactly what I said here. We are simply dividing this. In the normal cases, in the usual first examples, what we see is that we are basically dividing them, dividing by elements of S. So, this is the ideal generated by x. Let us look at one more example. A is f x comma y. So, this see this is you have said your intuition and I have accepted it, but you should write down a complete proof of this. When you have to write down an ideal is this, how do you do that? You have to prove both the inclusions. Which inclusion is trivial? This is contained here, is straightforward, right? Now, you have to prove this inclusion, for which you can simply use the property of variables, and when do you say two polynomials are equal? Yeah, so just comparing the degree and coefficients you get. So, but this proof is important in writing down. So, let us look at another example. Let me write this as and take my S to be y square. So, what would be I colon S? Can you tell me what would be I colon S? There is an obvious element there. Huh? x is there, right. So let's see if we can find the generators of this. X is there. Do we have something else? Can we think of some other element? See here, you have to look at maybe I will see, you have to look, see we have to divide all the elements of I by y square and see what are the elements. Now from here, can you think of elements that you can obtain from here? X cube y, x power 4 y, and so on, right. You multiply this element by x, x square, x cube, and so on, you get this. Another possibility is x square, y square, x square, y cube, x square, y power 4, and so on, right. These are another set of elements in this ideal. Another set is combination of these two, x cube y square, right, and then again x power 4 y cube, and so on. Similarly for this one. So when you divide by y square, this none of them is divisible by y square, right. This has only y term there. So you can't really divide this by y square. Now dividing this by y square, what do you get? X square, x square y, x square y square. But when we are considering the ideal and we are trying to specify the generators of the ideal, do we need to mention x square y, x square y square, and so on? Because if x square is there, x square y is there, and if that is there, x square y square is there, and so on. So we only need to make sure that this element is there. But now from the other one, we already know x is there. So x square is also superfluous, because that you can obtain from x. So the question is there anything more here? Okay. So exercise, find I colon s in this example, okay. And find means you have to prove, okay. Whatever the ideal, if you are trying to prove that it is generated by x, and you have, if you are saying that it is indeed x, then you have to prove that this is equal, okay. Fine. Now let us look at one observation. Suppose J is the ideal generated by the set S. Okay, before that, let me suppose you have S1 is contained in S2. What can you, how do you compare I colon S1 and I colon S2? I colon S2 is contained in I colon S1, right? Because this ideal takes everything in S2 inside I. In particular, it will take S1 inside I. So therefore, if X belongs to this set, it has to be here. So therefore, we have the reverse inclusion. Now, let J be the ideal generated by S. Do you know the notion ideal generated by a set? Set of all polynomial combinations of or A linear combinations of elements of S. That is basically the ideal generated by S. Now, can you compare I colon S and I colon J? Of course, the first remark says that this inclusion is true. Is the other inclusion also true? From here, this is contained here because J contains S. J contains S, therefore, I colon S contains I colon J. Now, what about this one? Is this true? Let us start with an element here, okay, X in I colon S. Okay. Now, we want to check whether it is in I colon J. Now, take any element of any element in J. This means this element Y is of the form some AI Xi or AI Si I from some finite summation AI belong to A and Si belong to S. Any element in J is of that form. Now, do you see the result? What can you say about Xy? This is summation AI Xsi I from 1 to n. What can you say about Xsi? We have started with X in I colon S, which means X multiply every element of S inside I, which means all these are in I. Therefore, what can you say about this linear combination? That is again I, because AI is in I, AI is in A, XSI is in I is an ideal, therefore, this is in ideal, this is in the ideal I, therefore, the whole summation is in the ideal I. Therefore, this belongs to I. So, what have we proved? For any X in I colon S and any Y in J, XY belongs to I, which means X belongs to I colon J. This implies X belongs to I colon J, or in other words, I colon J is equal to I colon S. So, when we are taking colon, whether we take a set or the ideal generated by that set, they are the same. Okay. So, let me give you 1 or 2 exercises. Find 6z colon 3z 24z colon 5z. What would be 24z colon 5z? Yeah, think about this. It's okay. Find these ones. There is one important colon or if X is in A, then this, so this is the, I will write this as simply 0 instead of 0 with bracket. 0 is an ideal, the 0 ideal, I will write it as just simply 0. Then this is called the annihilator of x, okay. So, if you look at Z6, what is the annihilator of 3 bar? So, what would be this? It will be an ideal, right? If you simply say 2 bar, that is not enough. Yeah, there will be 0 certainly, then 2 bar, anything more? 4 bar, right? That will also be there. Okay. Let us look at some more properties of first observation. Can you relate I and I colon S? Every element of I will multiply S inside I, right. So, this is always the case. Now, if you take two ideals, I colon J1 colon J2, so think of the the division that I said. I am first dividing by all elements of J1 and then dividing by all elements of J2. That should be same as I take the product of J1 and J2 and divide. In some sense, say if you look at the integers, and in the case of ideals this is true, the colon operation indeed behave like that. Okay. So, this is I mean this is something one can the simple ideal theoretic verification, which I will leave it to you to check. From this first one, from one it follows that if I look at I colon S multiply with I, this is contained in I, right. I1 intersection I2 colon S. So, if I take an element x which multiplies everything inside the intersection, this will, so if x s is contained in I1 intersection I2, which means x s is contained in I1 and x s is contained in I2, therefore, it is in the intersection. Now, suppose x s is in the intersection, which means x s is I1 in I1, x s is in I2, therefore, it is in the intersection, x s is in I1 intersection I2, therefore, it is here. So, these two are equal. Okay. We will see some more uses of this colon and so on later in the course. Let us move on to study another type of ideals called radical ideal. So, radical of an ideal. So, let I be an ideal in A, then I look at the set R of I to be set of all x in A such that x power n belongs to I for some n. Okay. I am looking at all the elements in I, all the elements in A whose some power belongs to I, or in other words, if you look at the ring A mod I, can you identify this set? In A mod I am looking at all the elements whose some power is in I, but if an element is in I, what would be its image here? It would be 0, right? Or in other words, we are looking at all nilpotent elements, or in other words, this is the nil radical there, or in other words, we are looking at, suppose this is our natural map, then a radical of I is nothing but the inverse image of the nil radical of A mod I. Right? I am looking at all elements. So, if I take an element x plus I whose nilpotent in A mod I, what does that mean? X plus I whole power n is 0 plus I, or in other words, x plus n belongs to I, which is similarly, if x plus x power n belongs to I, then x plus I is a nilpotent element here in A mod I. Therefore, the radical of ideal is nothing but the inverse image of nil radical in A mod I. So, therefore, this immediately tells you that I is an ideal. See, if you look at this definition, a priori there is no reason why this should be an ideal to start with, right. But now what we are seeing is that this is inverse image of an ideal. Inverse image of an ideal in a ring homomorphism is always an ideal. Therefore, this R of I is an ideal in Let us look at some simple examples. Let us take Z itself, okay. And I look at, let us say, my ideal I is 9Z. What is the radical of I? Can you identify some elements which are there in radical of I?
We can use that thing.
Yes.
Where A mod I will be Zn. I fully contained in that.
Yeah. So what are the nilpotent elements in Z mod 9Z? What are the nilpotent elements in Z mod 9Z? What is the nil radical of Z mod 9Z?
6 036.
036. So nil radical of Z9, this is 036. 6 times 6 is 0, right? So 6 square is 0, 3 square is 0, 0 is there always anyway. So what is its inverse image? Phi inverse of, what is its inverse image in Z? What is that ideal? What is the inverse image of this ideal? What is this ideal in Z9? Is Z9 a principal ideal ring? So what is the relation between ideals of A mod I and ideals of A? 1-to-1 correspondence with what? Ideals of
A containing I
are in 1-to-1 correspondence with ideals of A mod I. This is an ideal in A mod I. So what is the corresponding ideal in Z is my question. It should be an ideal containing which Z? What is I here? 9Z. It should be an ideal containing 9Z. What are the ideals containing NZ? If you take any n, what are the ideals containing NZ? When does an MZ contain NZ? When does NZ, when does this happen? This, if and only if M divides N. So what are the ideals containing 9Z? What are the divisors is my question. There are only 1, 3, 9, which means what are the possible ideals? 1, which is the whole ring, then 3Z, then 9Z. So what is the inverse image of this ideal? 3Z, right? So phi inverse of 0 bar, 3 bar, 6 bar is nothing but this. See, this is the ideal generated by 3 in Z9, right? So therefore this is 3Z. That's the radical of 9Z. Is this clear? Let's look at another example. I is 12Z. What is the radical of 12Z? So let's write 12. 2 square times 3. See, it will be an ideal generated by one element. So if you can identify one element, probably the least, whose some power belong to this ideal, you are through. Will 2z, will any power of 2 belong to this ideal? Will any pure power of 2 belong to this ideal? 2, 4, 8, 16, 32, 64, will any of them belong to this ideal? For any element to be in this ideal, 3 should divide. That is one necessary condition.
Minimum power of 2 should divide.
Yeah, 4 also should divide. I mean 12 should divide that integer. So therefore, we cannot think of, if you take say for example ideal generated by 2, that will not be the radical. Can you think of one element whose some power belongs to this ideal? 6. What is 6 square? 36. Does it belong to this one? Yes, right. This times 3, this is 2 square 3 square, which is 6 square. 6 square belongs to this one. Therefore, 6 belongs to radical of I. Now, can we say it is equal? For any, if I have an element, if I have an integer m in z such that m power n belongs to I, can you say something about this m? What are the possible prime factors of m? You should be able to say at least these are there. Can you say something of that sort?
Sir, up to m ki power n minus.
Sorry?
Up to m ki power n minus 1.
No, I am asking, can you tell me some prime factors of m? Prime factors of m, prime divisors of m. Can you think of one?
M by n.
No, that is not a prime factor. Can it be 5? For example, m equal to 5, can it be that? Can m be equal to 5? If I take m equal to 5, can any power of 5 belong to I? No. I is 12z, remember. So what should be some minimal, some you have to say some.
GCD between m and that I.
See, that is what I am asking. Give me some prime factors of m. 2 has to divide m, right? You cannot get a number which is not divisible by 2 and whose power belongs to this, because any element here is divisible by 2, right? M power n belongs to I means it is here, which means 2 has to divide m power n, which means 2 has to divide m. Similarly, 3 also divides m. 3 divides m power n, which means 3 divides m, which means 6 divides m. What I mean, we already said that 6 belongs to radical of I. Since this is an ideal, 6z is contained in radical of I. What we have observed here is that if any element belongs to radical of I, 6 should divide that element, or in other words, it is here. Okay. So this implies 2 has to divide m power n, 2 has to divide m, and this also implies 3 has to divide m power n, this implies 3 divides m. So, these two together implies that 6 divides m, or in other words this implies that m belongs to 6z. So, what we have proved is radical of I is 6z. So, now do you see the technique, at least in the case of z, if I have, if your n is p1 power alpha 1, n is p1 power alpha 1 up to p r power alpha r, then what is the radical of nz? Right, p1 to p r. Okay, so now let us look at some basic properties of radical of Can you compare I and radical of I? What is the definition? Radical of I is nothing but all elements in A whose some power belongs to I. So, taking n equal to 1 itself, or in other words, if you look at this definition, this is phi inverse of, this is an ideal, 0 belongs to this. What will be phi inverse of 0? Phi inverse of 0 is contained in phi inverse of the nil radical, which means I is contained in radical of I. If I is contained in J, then can you compare the radicals? Radical of I is contained in radical of J. If I is strictly contained in J, then can you say something here? Is this true? Will it be true? Look at the, yeah, we had two examples, 6z and, yeah, if you take 6z and 12z, both their radicals are 6z. Or if you look at this example, whatever the alpha 1 up to alpha r be, radical is going to be this. So, this is not true. Okay. If I take, I have already, you know, see radical of I, in some sense you can think of this as, you know, you take an element in I and taking the possible nth root, all possible nth roots of elements in I, whatever n be. Okay. So, once I have done that, your elements of R of I, you can't really take any more nth roots. So, if you apply this again, it should possibly not change. This is a simple verification. one containment is clear from the property 1, right. The right hand side is contained in the left hand side, this is here. Now can you say that this is here? If I take x is in radical of I, that means x power n belongs to radical of I, but that would imply that x power n whole power m belongs to I. So this is for some n and this is for some m, and that would imply that x power nm belongs to I. By definition, this implies that x belongs to radical of I. Okay. Radical of I is the whole ring if and only if I is 1. This is a simple verification. I will leave it to you to do this. I will do another property. How do you compare a radical of the product? This is same as radical of I intersection j, which is same as radical of I intersection radical of j. So let us first look at these two comparison. Can you see one of them contained in the other? I intersection j is contained in I, therefore radical of I intersection j is contained here. Similarly, it is contained here. Therefore, this is radical of I intersection j is contained in radical of I intersection radical of j from the first property. Now, if x belongs to I intersection radical of j, some power x power n belongs to I for some n, x power m belongs to j for some m. Now, can you think of a power which is in both I and j? Yeah, there are many candidates for that, x power nm, x power n plus m, even x power maximum of n and m, all of them will belong to. So, this implies x power n plus m or mn belongs to I intersection j, this implies x belongs to radical of I intersection j. So, therefore, this equality is true. Prove the other equality and stop. Again, can you see some equalities there? I mean inequalities, containment. This is contained here. Ij is contained in I, Ij is contained in j, therefore Ij is contained in the intersection, therefore radical of Ij is contained in radical of I intersection j by property 1. Now, suppose I have x belongs to a radical of I intersection j, this implies x power n belongs to I for some n and x power m belongs to j, oh sorry, I intersection j. So, x power n belongs to I as well as x power n belongs to j. Now, Now, can you tell me and x power n belongs to J? Now, can you give me an element in the product from these two information? X power 2n, this times this belongs to the product ideal, this belongs to I j, this implies x belongs to radical of I j. So, this implies and that we have already proved that this is contained in. Okay. So, we will see more properties of ideal on Wednesday.